Hey Earth Science kids, it's Mr. Yo, your science bro, and today we are talking all about orbits. Okay, first of all, an object captured by the gravitational field of a more massive object moves around that more massive object in an ellipse. All right? So an ellipse it's sort of like a circle that's been squished, and we have different measurements for ellipses. If it is more circular or if it is more squished. So we're going to show you how to do that today. Here I've sketched out an ellipse showing the important parts about how to measure it. So we have some important ideas here. These are the focal points, F1 and F2, the two focal points of an ellipse. This line here is the major axis. The major axis is the longest line you can draw in it. So an ellipse is defined by the distance between the foci, these 2 points here, divided by the length of the longest line you can draw on that ellipse, the major axis, divided by that. So right in your reference tables, you could see a formula. This formula is eccentricity, and that refers to the eccentricity of that ellipse. So the ellipse has an eccentricity defined by the distance between the foci divided by the length of the major axis. Let's see how that works out. So we would write the formula E equals d over L, distance between the foci, length of the major axis. Distance between the foci we've measured out, and that comes to 10.2 centimeters. This is usually measured to the nearest tenth of a centimeter. The length of this major axis comes out to 14.2 centimeters. When we do the division to the nearest thousandth place, which is what you're usually asked, the eccentricity comes out to be 0.718. If I were to get this more squished, this number would go up. It would get higher. If I were to get that more circular, that number would go down. It would get closer to 0. The largest this number can ever be is 1. So, orbits near and far. All right, so what we've done here then is draw an orbit and all the important things going on in an orbit. So if we had a planet orbiting a star, this is way more elliptical than our planet orbits the sun, and you know that from your daily life. Has the sun ever seemed to be huge in the sky and then super tiny in the sky? Nah, our sun always looks just about the same size in the sky, which means that our orbit must be very circular. So I've exaggerated this orbit tremendously. When we are close to the sun, think about that. When we're closest to the sun, all right, first of all, that point is described as the perihelion. Helion meaning sun. So perihelion means closest to the sun. So the point nearest to the sun, we've been falling all this time towards the sun, so we're going as fast as possible. Kinetic energy is a measure of your speed. So we have the highest kinetic energy possible, and we have the lowest potential energy. We cannot fall any closer to the sun than we are. So that's the lowest potential energy. So now as we pull away from the sun's gravity is pulling on us all the time, slowing us down. Our kinetic energy is turning into potential energy. Very much like if you are bouncing on a trampoline. When you bounce and you're first coming up, you're going very fast. You have a lot of kinetic energy, and as you go up and up and up above the trampoline, your kinetic energy is converted to potential energy. Now eventually you're up pretty high up above the trampoline. You have no speed, but you are going to because you have a lot of potential energy. You're going to use that energy to fall back and end up going fast again. So we're pulling away from the sun, getting slower and slower and slower. When we're farthest from the sun, we are at aphelion. Helion again, sun, ap meaning furthest away. So aphelion, we are as far from the sun as we can get. We are slow, going as slow as we're going to get. That means our kinetic energy is as small as possible, but we have a long way to fall back towards the sun, so we have the highest potential energy. Now we fall back towards the sun, falling the entire time, our potential converting to kinetic again, and we're getting as fast as possible. Notice F1, the first focal point, is the focus of, or is where the sun is. That's where the sun is. Look at F2 though. There's nothing there. It's not the moon or some other planet. It's just a mathematical point. Now, you would know it by however far F1 is from the orbit, F2 is from the other side of the orbit. So that's how they would define where F2 is. But that's the idea of what's happening as we move around an orbit. Now, I have drawn some example orbits here that we're going to measure and do some calculations on. All right, so I have some magnets here, and I have a rubber band. When I have the magnets at the points I've defined as F1A and F2A, I've already sketched this, but I'll show you how we would do that. Right? So we have this rubber band. I think I have the longer rubber band. So we have this rubber band, and we would use it to sketch all around this. And that would draw the shape we see as A here. And the foci are right here in blue. The shape is right here in blue. We could calculate the eccentricity here. Right, so why don't we just try that? We'll do some measurements. So if I measure from the center of these blue circles, F1 to F2, I come out to about, looks like about 3.3 centimeters. And the distance across that looks like to be about 13.1 centimeters. So what is that eccentricity going to be? We just use our handy calculator. 3.3 divided by 13.1. These are all in centimeters. The centimeters cancel. When I press equals, I get 0.251, but that's a 9. If I'm rounding it to the nearest thousandth, that means it's going to be 0.252. 252. 0.252. Excellent. Let's try and see what the eccentricity of B looks like. So I move these over to the locations I've defined as B. Use that rubber band on them. Now I can't go up nearly so far because they're much further apart. So now when I sketch that out, we come out with that. We'll move these off, measure it again. Okay, always in centimeters. So here it looks like I have about 6.4 centimeters. 0.4 centimeters. And the length of the major axis is, looks like 10.7 centimeters. 10.7 centimeters. When I do that calculation, 6.4 centimeters divided by 10.7 centimeters, that equals 0.598. You can see that that would stay point. So that would be 0.598. Right? Remember, the centimeters cancel, so there's no centimeters there, but 0.598. So you can see this is a higher number. The red one is a higher number than the blue one. You can see the red certainly looks like a more squished circle than the blue one. The blue one is starting to look almost circular. If it was a perfect circle, both of these would be in exactly the same point. So the distance between them would be 0. 0 divided by any number is going to be 0. So that means the eccentricity of a perfect circle is the number 0. That number 0 looks a whole lot like a circle, doesn't it? If it was as eccentric as possible, these numbers would be, these points would be far apart, and it would just be a line in between. That rubber band is stretched all the way, just a line in between them. That means your foci are also as far apart as your major axis. That means whatever number you have here is being divided by itself. That gives you the number 1. Number 1 looks like that straight line that orbit would be. So that's the idea of how to calculate those orbits. All right, and there's the idea of a circle, right? If this was 16.9 that we calculated here, that would be then divided by 16.9. Or I'm sorry, you would have no distance between them, and that would be divided by 16.9, so you would end up with 0. If we have F1 and F2 with a straight line there, it's 16.9 divided by 16.9. That would give you 1. So, if you have an eccentricity of 1, you have a straight line, right? If you have an eccentricity of 0, you have a perfect circle. So that's a pretty easy way, you would accept, to remember these things. The last thing we have here are Kepler's laws. Okay? And Kepler has 3 laws that go with this. Right? The first law is that all orbits are ellipses with the sun at one focus. Johannes Kepler was the first one to figure out what planets are doing in the shape of their orbits. Brilliant man. Absolutely brilliant man. So Kepler's 3 laws are all orbits are ellipses with the sun at one focus. A line joining the sun and a planet sweeps out equal areas in equal times was his second law. This is called the equal area law. Take a look at what that means. That means if that's the sun and that's the planet going around it, if it takes 30 days for it to go from there to there, that would sweep out area 1. Far away from the sun, it's going quite slowly. So 30 days would take it a shorter distance. That would be area 2. Area 1 equals area 2. And this is universal for all planets in all orbits. His third law, a little mathematical, that's the square of a planet's orbital period, t, is proportional to the cube of the semi-major axis of its orbit. Semi-major axis is simply half of the major axis. That would be r. So the law comes out like this. T squared is proportional to r cubed. What you need to understand is that it means simply if you know one of these things, you can easily calculate the other. So that was Kepler's third law. We started understanding orbits finally after Johannes Kepler gave us what we needed. Thank you very much. Have a lovely day. Hope you know orbits.